Going to look at another case of permutations, case 4, where instead of arranging all the objects in a line, we're going to arrange them in a circle. So the question is, what is the difference in placing in a line and placing in a circle? And basically it comes down to just the first object, how that first object is placed. You see, if we've got a line, there we go, we place some objects in a line, we've got a definite start and a definite finish to the line. All of those positions can be defined. The first position, the second position, and so on. But when you have a circle, here we go, there is no start or finish to a circle. So because of that, there really is only one way to put the first object, and that's in the circle. Because it doesn't matter where I put it in the circle, I can always rotate the circle and it can be in any position. So with the line, we've got 6 choices to place the first object, whereas with the circle, we only have 1, and that's to put it in the circle. So how does that affect our permutation? So in a line, we'd start off and say, well, the first object has got n spots to go. But in the circle, we'd say, well, there's 1 spot it can go. But then once it comes to the second object, it becomes the same. Because once an object's placed in the circle, now all the other positions can be defined. 1 to the right of that person, or 1 to the left of that person, and so on. So we can come back to n minus 1. And the third object would be the same. And so on all the way until we get to the last object. So the difference is basically n factorial, but we divide it by n, the number of ways we could have placed the first object. Well, in effect, that's just n minus 1 factorial. So if it's in a line, n factorial. If it's in a circle, we just take 1 off, n minus 1 factorial. So we've got a meeting room. Contains a round table. I suppose it doesn't really have to be round when you think about it. It could be a rectangle. You've still got chairs going around in a circle, but yeah, it's a round table. Committee of 10 people, and we've decided 3 of you teenagers can be in this committee. It's very generous of us. How many arrangements are there in which all 3 sit together? Because, you know, it's very intimidating being with us adults. So the 3 teenagers, oh yeah, we're going to be together. So how many ways can we do it? Well, look after the restriction first. So the first thing is the group of 3, let's work out how they're going to sit. 3 factorial. Still 3 factorial at this stage because we haven't placed them anywhere yet. It's just how many ways can we arrange those 3 people. But now it will be times 7 factorial. So now we've got 8 objects. The group of 3 plus 7 others. But we're placing them in a circle, so instead of being 8 factorial, it's 7 factorial. And there you go, we get 30,240. Okay, we're going to hold an election for the chairperson and the secretary of the committee. What's the probability that they're seated directly opposite each other? Well, if there were no restrictions all up, so that'll be the bottom of our fraction of the probability, 10 people in a circle, 9 factorial. Okay, let's sit the president down. He can choose, or she can choose, which seat they want. They're the president. In fact, they don't like the name chairperson. How come I call it president instead of chairperson? Anyway, okay, so they choose which seat, but it's in a circle, so really they've only got one choice. They're going to sit in the circle. But now the secretary has to sit opposite them, so they only have one choice. We will now arrange the other 8 people. Yes, it's in a circle, but because there's already 2 people sitting in the circle, the positions are defined, so we treat it like a line. 8 factorial. So our probability will be 1 times 1 times 8 factorial or 9 factorial, which simplifies down to be 1/9. Of course, we could have done that by logic. President sits down, what's the chance that the secretary sits directly opposite? Well, there's 9 chairs, only one of them is directly opposite, so there's a 1 in 9 chance. So as I say, sometimes just using logic is quicker. Here's an old HSC question. So 7 people sitting around a table. Starts off, how many are possible? So no restrictions. How many are possible? Oh, well, 7 people, but it's in a circle, 6 factorial. Now 2 people, Kevin and Jill, they refuse to sit next to each other. So how many arrangements are now possible? This is another one where the complementary idea works better. It's going to be a lot quicker to work out how many ways they are together than try and work out all the possibilities when they're not together. So let's have a look at how many when they are together. So Kevin and Jill are together. They work out their arrangement, 2 factorial. Now we're arranging 6 objects. Our group of Kevin and Jill and 5 others. 6 objects, but in a circle, 5 factorial. So 240 ways. But we want the complement, therefore we take it away from the total number of possibilities, and we end up with 480 arrangements. Here's just a little flow chart of sort of the thinking of how, if we don't know how to approach the problem, what should we be using? Is it a permutation? Is it a combination? I forget where I found it, but I thought, it's not too bad. All right, there we go. 14G.